Hello and welcome back to Let's Code Physics. Last episode we were able to successfully create a loop of wires that carried electrons around in a circuit. So starting today we can take a look at some of the neat things that circuits can do. We can start to model different circuit components. I'm working on modeling resistors to where we can have resistors in series and in parallel and obey all the voltage and current rules for those. But for today, I wanted to try modeling a capacitor. A capacitor is basically a circuit component that traps electrons, that makes it very difficult for electrons to pass from one side of the capacitor to another, with the idea being that you want to store charge on either side of the capacitor and have an electric field built up in between. So capacitor stores charge, therefore it also stores energy because it's storing a potential difference between the two sides. So what I've done is I've taken our loop from before. I've got the bottom wire and the right wire and the left wire. And I've taken our top wire and I've split it in half. So instead of being 10 units long, it's going to only be 3 units long on one side, 3 units long on the other side. That gives us a 4-unit gap in the middle there at the top of the circuit. And that's where I'm placing the capacitor plates. Is basically over connected to the top wire. So you'll have the 2 top wires, and then you'll have the capacitor plates. So you'll notice I'm making the capacitor plates wider than they are long. So they're going to be very thin, very wide rectangular prisms. And so rather than being wires, these are going to be like blocks up there on the screen. And so these things are going to be wide in the Z direction. So in order to accommodate that, I've added scattering and bouncing in the Z direction. So before we were only scattering in the XY plane, and so we just needed one angle. Now we're scattering in 3 dimensions, so we need 2 angles. One's going to be the angle for the XY plane, the other is going to be the angle from the Z axis. And one of the things about this system called spherical coordinates is when you have these 2 angles, you only need one to run from 0 to 2 pi. The other one only needs to run from 0 to pi, and you've got the entire space covered. Otherwise, you're double counting if you have them both go from 0 to 2 pi. And then down here we've got the electron velocity randomized to both of those. These are just the spherical coordinate transformation. So x is given by sine of the second angle times cosine of the first angle. Oh, actually I have that backwards, don't I? Not that it really matters all that much, but I just realized I have these backwards. So let me fix that. The code has been working without that corrected. Okay, I had this one correct. It's the other 2 that I. Okay, so basically I flipped the sine and cosine. I see now what I did. Okay, yeah, because no, actually I did have that correct. My bad. Okay, I just put the sine first. Okay, never mind. And then for symmetry's sake, we'll change that back. Yeah, because these 2 need to go like sine of the azimuthal angle and then cosine and sine of the planar angle. Okay, there we go. All right, I've got my bearings now. A little navigation joke there. And then we're doing a bouncing off of the sides in the Z direction. We're calling those the front and the back sides. Not really too much to show there. It's basically the same thing like we had before. What that also means is I had to add a front and a back to the wire class. Pretty straightforward like we've been doing with the others. And so what I've done here is I've got these 2 capacitor plates. Again, they're going to be wider, so they're going to be sticking way out in the Z direction. And I'm not putting any electrons in the plates initially. I'd like to add in a minute a count of the number of electrons that are stored in the capacitor. And so we're not putting any electrons in the plates. Another thing I changed just for consistency's sake is instead of having a fixed number of electrons in each wire, I'm having the number of electrons scale with the length of the wire. So this is really now number of electrons per length of the wire. So because I've got these 2 shorter wires now, for the top, and it doesn't make sense for them to start out with the same number of electrons as these much longer wires on the other sides. And so I've changed that now to number of electrons per unit length. And then we're just multiplying that by the length of each wire over here. So that makes it a little bit more consistent. Let's take a look at the animation for this thing. Okay, so here's our two, let's worry about the graph in a second. Here's our two giant plates. So we've got a plate over here, a plate over here. So current is flowing around in the counterclockwise direction, meaning that this plate is going to have no electrons. This plate is going to eventually collect all of the electrons. Because this thing is so thin and so wide, it's very difficult for electrons to escape from this plate, because once they scatter out in this direction, it's very unlikely that they'll scatter back this way and end up in the wire and try to scatter back around the circuit. So given enough time, this thing is going to collect pretty much all of the electrons. We've got a few, we've got a few stragglers down in the bottom wire, but again, because of the electric field, these things are eventually going to collect in here. And this is basically, let me zoom out a little bit. This is essentially what happens in a capacitor, is that you run a current around the circuit, and charge is going to build, or negative charge is going to build up on the capacitor plate over here. What that means is that you've got bare nuclei sitting over here. You've got nuclei, or you've got atoms that are missing electrons from over here, because we did have the charge nicely distributed before. But now the atoms over here are missing the electrons that traveled over here. So we've got a net negative charge on this side, and we have a net positive charge on this side. I don't have any visual representation yet of the positive charges. I might add that in a future version. I think everybody is over on the right plate now. And so what you would have is net positive charge on this side, net negative charge on this side, and that gives you an electric field in between the two. That gives you a pretty much uniform electric field going from the positive charges over here to the negative charges over here. That electric field stores energy, and so you've got energy stored in the capacitor right now, which is pretty cool. Another way we can check our results is that if you do the math, which I don't really feel like showing you this morning, but if you do the math of how this current is supposed to behave, it should die down exponentially. So it should go down like e to the negative t. And so apart from our initial ramp up, when things start to level out, we do have a pretty nice exponential decay here for our average current, which is pretty cool. That we've been able to successfully match that. So that's a pretty neat result. We've been able to confirm that. Another thing that I would like to count is that I would like to graph is the number of electrons in that plate. So let's see. So and actually I've got this one should be pointing to the right. Not that it really matters because I don't have any electrons in there. But what I'd like to do is count the number of electrons in this plate where the electrons are being collected. So rather than plot the average speed like we're currently doing, what I'd like to do is plot, as a function of time, the number of electrons in that wire. So what I need to do is count the number of electrons in that wire. So let's do that. Actually, don't I count that somewhere up here? Oh no, I guess I don't, but I could do that here. So let's do this because we're already counting W in wire list. So let's add to our wire class a number of electrons. Self.num electrons equal to 0. Cool, so that way I can keep track of the number of electrons in each wire. And so what I can do here is for W in wire list, W.num electrons equals 0. And then I can do, oh no wait, I don't want to do that here. I want to add the number of, Okay, yeah. This will be a rough approximation. We'll say that w.num underscore electrons plus equals 1. So we'll add 1 to each one, and then within each... Oh, I do have something. I have this in wire list. Okay, I knew I had that somewhere. Let's make that a global then. Global in wire. Copy that. We'll paste that down here. I knew I had that set up at some point. I just haven't been using it for something. Okay, so we've got in underscore in wire. So this is the number of electrons in each wire. And so here we're setting that equal to 0. Lovely, lovely. And so what I can do here is I can say, oh wait, but I can't access that here. Okay, never mind. Rather than that, let's get rid of the stuff having to do with in wire. Not the way I want to do that. I do want it to be the thing attached to the thing attached to the wire itself. So let's say w.num electrons equals 0 so that we can count. And then down here we'll have w.num underscore electrons plus equal 1. And so then, oh, okay, so I did figure out how to do that there. Okay, well, fine, then we'll just, then let's take out that, I guess. I'd rather have it attached to the wire. That's a little bit more direct of a calculation. There we go. Okay, do I have any more references to in wire? Okay. Oh, that's what I was doing. I had it in a print statement. We can get rid of that there. I don't need that diagnostic anymore. So then what I can do here is graph. Let's see. We'll go wire underscore list of the last one. So that's going to be number 0, 1, 2, 3, 4, 5, 6. Of 6 dot num electrons. Close up. And let's see how that behaves. So according to the model, that should grow exponentially. And it is not changing at all. That's weird. Okay. Let's see. So we've got num electrons there. Why don't you print for me, please? Wire underscore list of 6 dot num underscore electrons. Give me an idea of what's going on in there. I'm looking at my print values. 180. No, there are not 180 electrons in there. There might be 180 electrons total. Let's see here. How am I doing this? So we've got num underscore electrons there. I've got num underscore electrons being initialized to 0 at the beginning there. Oh, oops. I'm increasing that by 1 no matter what. Oh, okay. Oops. So that is the total number of electrons. Oops. Okay, so then I guess what I want to do here is I want to put it in else. Then put in this. There we go. Alrighty. Okay, cool. So now we'll only add it if the electron is in that wire. Okay, yeah, so we start out with 0. Still have 0. There we go. We get a spike up. Okay, cool. Yeah, so what you're seeing there is the jaggedness of the electrons, bouncing in and out. This will run a little bit faster if I take out that pesky print statement that I no longer need. So let's take out this statement. There we go. Okay, cool. So yeah, it is running a little bit faster now. Okay, cool. So you notice it's jumping up and down because they'll go in and out, but basically it's there in the capacitor, meaning they're past the entry point. Scatter back because they have to scatter back to this point and then back in this direction. Oh, this is a lovely function, isn't this? Reminds me of the Cantor function, I think. In the So in the theory, this is supposed to grow like 1 minus e to the negative t. So it's supposed to have kind of like this upside down exponential growth thing. So it should be leveling off, and we've seen that it'll level off before. But basically, its slope should be decreasing pretty consistently. That doesn't seem to be happening too much in this case. So in the first 10 seconds, we went up by 10. In the second 10 seconds, we went up by about 10 again. In the next 10 seconds. Okay, so this thing has a pretty consistent slope. That might be an artifact of the fact that I've got such a finite number of electrons, whereas in a metal, number of electrons is basically infinite. You know, you're basically dealing with a fluid. So I might need to add more electrons. I might need to make these wires longer as well, because they would need to be long compared to the size of the capacitor for them to take longer to get there. But, I mean, in the end, you do get it to level off. While this, I guess you could fit this with an exponential curve. It's just it doesn't look terribly exponential till about this point right here. But you do get that leveling off like you expect. This is sort of what you would get for the charge if you were to do the charge in this experiment. So that's kind of cool. Another thing that you can change is the amount of time that that's supposed to take. So if I wanted to change the resistivity of this system, so this is called an RC circuit because the time is dependent on the resistance and the capacitance. So let's try changing the resistivity of these wires. I don't really need to worry about the resistance in the capacitor. That's kind of a meaningless quantity. So this took about 40 seconds for this thing to level off. I've changed the resistivity, so that should change the amount of time it takes for it to level off because the electrons can get there faster. So let's see if we get a significant change in the I guess that's called the charging time, is it? I mean, we call it the RC constant usually, but I guess in layman's terms that would be the charging time. So let's take a look here. We've got quite a few in the capacitor now. They're coming around the corner here. Let's see. Yeah, so the way it's supposed to work is that the time is equal to, I think it's R times C, the resistance times the capacitance. No, wait, that doesn't make sense. It needs to be... okay, I'll have to look that up. I'll tell you what, I will look that up and I will post an answer to that right here. I should know these things, but I haven't taught an E&M class in a while. Okay, so we've got nearly all the electrons in. It's starting to level off, so we've got kind of this sharp peak here. I know it still hasn't leveled off until about 40. I'm going to blame that on the fact that I don't have a consistent way of implementing the resistance yet. Although I suppose it does, I mean, although it peaks at about 40, it does start to level off a little bit better. I think if we compare those two graphs, this one starts to, this one starts to level off a little bit earlier. Okay, cool. So that gives us an idea of how an RC circuit behaves. Hopefully, if you're studying circuits, this gives you a visualization of what's happening with a capacitor. I know you don't get to see the electrons actually flowing around. So this shows you what's happening in that parallel plate capacitor that you're working with. So this has been a fun experiment. Let's continue exploring more about circuits next time. Thanks so much for watching. I will see you next time. Bye-bye.